Hi, this lesson is about limits at infinity and asymptotes. So we'll be talking specifically about vertical and horizontal asymptotes. So what is an asymptote? In general, an asymptote is a line that a curve approaches but doesn't touch. A vertical asymptote usually occurs at values of the domain that result in division by zero. So you'll see vertical asymptotes in rational functions, or some rational functions, and some of your trigonometric functions. And a horizontal asymptote exists if f of x approaches some value, some finite value L, as x approaches plus or minus infinity. And if that's true, then you say that y equal to L is your horizontal asymptote. So not all functions have asymptotes. Not all functions will have both vertical and horizontal asymptotes. We also have a scenario where you have something called a hole in the graph of a function, and that occurs at values of x associated where there's a common factor in the numerator and denominator of a rational function. All right, so let's study some of this. So we want to find vertical and horizontal asymptotes for this function. This is a rational function with a second degree polynomial in the numerator and also in the denominator. So to find our vertical asymptote, we're going to set our denominator equal to 0, which basically means I need to solve this quadratic equation. It's factorable. It works out to be 2x minus 1 and x plus 1. And if you set them each factor equal to 0, you get two solutions, but those solutions represent vertical asymptotes, which I am abbreviating as VAs. So I have a vertical asymptote at 1/2 and another one at -1/2. Now to find my horizontal asymptote, which I'm abbreviating as HA, we're going to take the limit as x approaches infinity of your function. And f of x, remember, is this rational function. So the algebraic way to show how to come up with your horizontal asymptote is to look at the highest exponent in the denominator and multiply numerator and denominator by the reciprocal of that, or divide by x squared. And when you do that and you distribute it across your rational function, you get this result. You get 1 minus 2 over x plus 1 over x squared over 2 plus 1 over x minus 1 over x squared. But as x approaches infinity, all of these fractions, so minus 2 over x, 1 over x squared, 1 over x, and minus 1 over x squared, as x approaches infinity, all of these expressions approach 0. So that just leaves you with a value of 1/2. And so therefore, y equal to 1/2 is your horizontal asymptote. All right, so let's move on. We're going to evaluate the limit of this expression as x approaches infinity of another rational function x minus 1 and 7x plus 4. All right, so as I mentioned above, you look at the denominator, look at the variable with the highest exponent, and then multiply by the reciprocal of that, which is what you see here. When you distribute that, you get this expression, 1 minus 1 over x over 7 plus 4 over x. But just as I mentioned in the last example, as x approaches infinity, the minus 1 over x and the 4 over x, they both go to 0. So minus 1 over a very large number is a very small number, and you can try doing that on a calculator. Do minus 1 over 100, and then try minus 1 over 10,000, and then you can try another one, minus 1 over a million, and you'll see that the value keeps getting smaller and smaller. So when you have minus 1 over infinity, conceptually, that should be a very tiny number getting closer and closer to 0. And the same thing happens with 4 over x. that keeps getting smaller and smaller. So you're basically left with just 1 over 7. So if you were asked what is the horizontal asymptote of this problem, the horizontal asymptote is y equal to 1/7. Okay. So in general, the rule to find horizontal asymptotes it all has to do with degrees of the numerator and the denominator. And so this is a shortcut to what I just mentioned. To evaluate the limit as x approaches positive or negative infinity of a rational function, you can follow these guidelines. When the degree in the numerator and the denominator are the same, like they were in this example, they were both a degree of 1, and in this example, they were both a degree of 2, then your horizontal asymptote is the ratio of the leading coefficients of f of x and g of x. So here, the leading coefficient was 1 and 2, so that's why my horizontal asymptote was 1 over 2. And in the second example, my leading coefficient was 1 and 7, so my horizontal asymptote was 1 over 7. Okay, so that's only true when your degrees are the same in the numerator and the denominator. If you look at this scenario where your degree in the numerator is less than the degree in the denominator, in that case, your horizontal asymptote is always going to be y equal to 0. And in the last scenario, if the degree in the numerator is greater than the degree in the denominator, then you will have no horizontal asymptote. So that's possible as well. So what are the exceptions here? So that's when you have a hole. So there's an exception to the guidelines above, which is when there is a hole in the graph. And the way you determine if there's holes in the graph, you can see here in the first example, is by looking at your expression. So this would be a scenario where the degree on top is bigger than the degree on the bottom. So that would mean there's no horizontal asymptote, which is true, but more specifically, this one actually has a hole in the graph. And the way you find the hole is to actually factor the numerator and denominator as much as possible. Here, only the numerator is factorable, and when you do that, you get this result. So I get x plus 2x minus 2. But notice that the x plus 2 in the numerator and the denominator cancel. When that happens, you're going to get a hole in the graph. And the hole occurs wherever the solution to that common factor occurs. And so that would be at x equal to negative 2. So x equal to negative 2 has a hole, but where you know what the hole is by taking the limit as x approaches negative 2 and plugging it into what's left, which is the x minus 2. So when you plug that in, you get negative 4. So you have a hole at negative 2, negative 4. And so therefore there is no vertical asymptote for this problem because there is nothing in the denominator once you cancel, but you do have a hole at negative 2, negative 4, and there's also no horizontal asymptote. All right, so let's look at another one that has a hole. Here, according to the guidelines above, I have the same degree in the numerator and the denominator. So if you followed those guidelines, you would say that you have a horizontal asymptote at this ratio 2 over 2, which is 1. But that's not actually true. So we're going to factor both of these. So they factor into what you see here below. And then you can see that they have a common factor of 2x minus 1, which cancel. And so again, at that expression that they have in common, that's where your hole exists. If you were to solve 2x minus 1, that means that it has a hole at 1/2. And the factor that's left is this one. And so therefore then there is a vertical asymptote at negative 1. And if you needed to know where the hole is, so if you were graphing, it would be helpful to know that, you would plug in that 1/2 into what's left. So you have a hole at x equal to 1/2, but your y would be 1/2 minus 5 over 1/2 plus 1. So this is negative 4.5 over 1.5, which you would then simplify, and that would give you your y value. Okay, so let's look at something other than a polynomial. Here I have an e to the x in both the numerator and the denominator. We want to find the horizontal asymptote or asymptotes of this rational function. So I'm going to look at taking the limit as x approaches infinity and as x approaches negative infinity. Now, as x approaches infinity, it's helpful to know what the behavior of e to the x is. So as x approaches infinity, e to the x gets very, very large very quickly. So the numerator is infinity, but e to the negative x, remember, as x approaches infinity of e to the negative x, well, that's equal to as x approaches infinity, this is 1 over e to the x, which is basically 1 over a very large number, which is equal to 0, which is why here you just have 1 over 0. So infinity over 1 means that it approaches infinity. Remember, you don't have a horizontal asymptote unless the limit as x approaches infinity converges to a finite number. Infinity is not a finite number, therefore the limit does not exist there. There is no horizontal asymptote as x approaches infinity. Now let's look at it from the other perspective, as x approaches negative infinity. So as x approaches negative infinity, my numerator is going to approach 0, because remember, as this goes to negative infinity, this is actually e to the negative infinity, which basically brings us back to this. You end up with 0. But here, as x approaches negative infinity, e to the negative x, when you plug in negative infinity, well, that'll just be e to the infinity. So you have 0 over infinity, which is equal to 0. So therefore, y equal to 0, that's a finite number. And therefore, I do have one horizontal asymptote at y equal to 0. All right, so let's find all of the asymptotes and possible holes in this next rational function, which is y equal to x plus 5 over x squared minus 5. All right, so let's see what this looks like when I factor this completely. So when I factor the denominator, you can see that I have a common factor of x plus 5. And since that is the case, that means that I'm only left with 1 over x minus 5, which means I have a vertical asymptote at the solution of that denominator, which is x equal to 5. But I have a hole at the solution for the common factor, which is negative 5. And if you plug in negative 5 into what's left, which is this, you have a hole at 1 over negative 5 minus 5. So that means I have a hole at negative 5 and a y value of negative 1/10. Right? And again, that's helpful when you're graphing to know where to put that open circle. I have a horizontal asymptote. I can take my limit as x approaches infinity of x plus 5 over x squared minus 5. If I follow that table that I had above, the degree in the denominator is bigger than the degree in the numerator, so therefore I will have a horizontal asymptote at y equal to 0. You could also apply the technique that I did on the other problems, which is to multiply through by the reciprocal of the highest degree in the denominator. And if you do that, you should also get 0 as a result. So I'll have 1 over x plus 5 over x squared over 1 minus 5 over x squared. So remember, all of these fractions go to 0 as x approaches infinity. So you have 0 over 1, which is equal to 0. So again, there's your horizontal asymptote. Okay, so our next example is going to have a logarithm in it. So before I do that, I want to remind you of the rules for logarithms. Remember, every exponential expression can get rewritten as a logarithmic expression. So y equal to b to the x can be rewritten as x equal to log base b of y. So where you call this b to the x the exponential form, and the other x equal to log base b of y is your logarithmic form. There's lots of rules and definitions regarding logarithms. So remember that log base b of 1, no matter what the base is always equal to 0. Log base b of b is equal to 1. Log base b of b to the n is equal to n. And then there's properties. These are called logarithmic properties or laws. Log base b of x to the n is the same as n log base b of x. In other words, this n goes in front. Log base b of x times y. So when you're multiplying two expressions, that's the same as taking the sum of the logarithms. And the same is true for a quotient. Products and quotients are opposite operations, so are sums and differences. So the log base b of x divided by y is equivalent to the log base b of x minus the log base b of y. All right, so we're going to use one or more of these properties or definitions in order to evaluate this limit. So we have the limit as t approaches infinity of ln of t squared minus 1 minus ln of 4 plus t squared. So I'm going to apply this property to this logarithm. So I'm going to rewrite that difference as a quotient. So this gets rewritten in this way. And then I can use the trick that I used in a few examples, which is to multiply the numerator and the denominator of this rational expression here by the reciprocal of the variable term with the highest exponent, which is 1 over t squared. So if I distribute that, you get what you see here. I have the limit as t approaches infinity of ln of 1 minus 1 over t squared divided by 4 over t squared plus 1. All right, so these two expressions as t approaches infinity go to 0. So you're really just left with ln of 1. But remember, the log base b of 1 is 0. Here, the base of ln is e, so that same definition is true. So ln of 1 is also 0. So your limit equals 0. Okay, so here we have a radical expression. And we want to evaluate the limit as x approaches infinity of square root of 9x to the fourth minus x over x squared plus 1, and then evaluate the same function as x approaches negative infinity. So I have the limit as x approaches infinity here of my function. And so remember, the trick is to multiply by the reciprocal of the expression with the highest exponent in the denominator. But that's a problem because I can't distribute 1 over x squared here. You can't distribute 1 over x squared to a radical. You need to actually be able to multiply by another radical. But notice that these two are actually equal to each other. So 1 over x to the fourth equals 1 over x squared. And you always have to be multiplying by 1. So you're just going to rewrite 1 over x squared as the square root of 1 over x to the fourth. And now you can distribute across that numerator. And when you do, you get this expression here. And then just like I mentioned in the previous examples, the fractions, the minus 1 over x cubed and the 1 over x squared, as x approaches infinity, those will both go to 0. So you're left with just root 9 over 1, which is equal to 3. So my limit value is 3. And again, if I were to graph this, that would mean that I have a horizontal asymptote at y equal to 3. Okay, if I do the same thing as x approaches negative infinity, well, nothing really changes because as x approaches negative infinity, both of these expressions just go to 1 because when you raise negative infinity to the 4th power or squared, that's the same behavior as positive infinity because they're even exponents. And so when you work that all out, you actually get the same result, which is 3. So you get the same behavior from positive or negative infinity. Now, in this next example, I have another radical, but my behavior is going to be a little bit different because here I have a second degree polynomial, but here I just have a first degree polynomial. So let me show you how things will work out a little differently. So here I'm going to look for a horizontal asymptote. I'm going to take my limit as x approaches infinity. So again, this is the driver. The reciprocal of x is 1 over x. But again, I can't multiply the numerator by 1 over x because I have a radical. So 1 over x is the same as the square root of 1 over x squared. And now I can distribute. And when I distribute, you get this expression. As x approaches infinity, the fractions, the minus 1 over x squared and the 1 over x, they both go to 0. So I'm just left with root 4 over 1, which is equal to 2. So I have a horizontal asymptote at y equal to 2. But as x approaches negative infinity, things change. As x approaches negative infinity, this is a negative expression. Because 1 over x as x approaches negative infinity is a negative expression. But the square root of 1 over x squared, well, because I'm squaring negative infinity, that's a positive expression. Remember, you always have to multiply by 1. So in order to make this 1 as x approaches infinity, I have to put a negative in front of the radical. Otherwise, this expression on its own will be negative 1, because I have a negative in the denominator, a positive in the numerator. So I have to force it to be 1, so you put a negative in front. So when you distribute this expression across, this negative goes in front, and so you end up with a value of negative 2. So you actually have 2 horizontal asymptotes, one at positive 2 and one at negative 2. So we have a slightly different behavior because I have an even and an odd degree than I did in the previous example. Now let's look for a vertical asymptote. My vertical asymptote is where my denominator is 0 and my denominator is x plus 1. You solve it and you get x equal to negative 1. So I have a vertical asymptote at x equal to negative 1. And if I do a sign analysis of this behavior, if you take the limit as x approaches negative 1 from the left and from the right, and you look at what the behavior of the function is, here, when you approach negative 1 from the left, this will be a negative number. A small negative number and a very small negative number means that this entire expression approaches negative infinity. And as I approach negative 1 from the right, then I get x plus 1 from the right means that I get a small positive number here. So that means that the entire thing approaches positive infinity. So the radical over a number close to negative 1 from the right would be something like negative 0.9999. And so negative 0.999 plus 1 gives you a small positive number, and a number on top divided by a small positive number blows up, becomes a very large number, so we get infinity. So you can try that with a calculator, plug in different numbers so that you can confirm for yourself that you get a number approaching negative infinity as x approaches -1 from the left, but you get a very large number as x approaches -1 from the right. All right, so that's your lesson. Try the homework. Good luck.